All right, here's the latest design that I've been working on. I had to take a few weeks off while I printed some things for my son's robotics club, but now I'm back at it. And this is the latest design. I've got it printed in two different types of NinjaFlex. Now this blue stuff is pretty old, but I notice it's much stiffer than the new stuff, but I don't know if it's because it's old or the clear stuff just happens to be a bit softer. And I've got another one here just to make sure that it wasn't a one-off fluke. They're exactly the same. So let's have a look at the force curve on this one. And what I'm going for here for reference is an IBM beam spring, and I've got this one here as a reference. I just knocked it over. But here, let's have a look at the force curve. Actually, I went too fast. So I'm going down. There it inverts right around 60, and it actually holds about 38. It's hard for me to do this with one hand at this angle, but it converts about 60, and it inverts, and the minimum force required after that is about 38, 40-ish. I should say it's 40-ish, and that's with the blue spring, and the identical spring, but in clear NinjaFlex is considerably. Let me do a tear here. Considerably lighter feel. Like I said, I'm not sure why that is, but go down a little bit. You can see it inverts right around 33. Very, very gentle. And that might be like I might have just done too good of a job trimming or something like that, or it could be this keycap's a little different than that other one, and that's probably why. So let's take this one apart because I know this keycap happens to be quite a bit loose. Put it over here on my 3D printer where the lighting is great. So I'm just gonna hit the phone and turn it sideways. Let's take this one off so you can see the parts. It's hard to get this out. Well, you get the idea. This part here is just the sheath that goes around the stem, and it's printed flat like that so that the layer lines run this direction. And here's the stem. It too prints flat like that with the layer lines running this way. So you can imagine that they don't really rub up against each other in a perpendicular fashion. They're all parallel to each other, which makes it quite smooth, smooth action. And I've got I think it's 0.25 millimeter tolerance here. It is a little bit wobbly, but it's nothing. I don't know. It doesn't really matter to me, honestly. And it does not bind, and I'll demonstrate that in a minute. And this is the spring, and this is turned inside out. Let me turn it right side out, like how it prints. Just a moment here. So it prints like that. Well, it doesn't print curved like that. It prints as a perfect rectangle. So it prints like that. And then when you invert it, turn it inside out, it gets considerably springier. And then we just take a keycap. Now this one's got a sort of rectangular stem, but it works. You know, it's got a circle there. This is a standard cherry, for reference. We just sort of. This one's a little bit wider than a normal cherry, so I designed it for a cherry. So it takes a little bit of finagling to get it on there. Just a second, because I've made an improved keycap design since I made this particular keycap. From a stem assembly standpoint. Alright, I gotta take it away from the camera for a second. Alright, come on, let's get on there. There we go. Now I'm gonna turn it sideways. And let's put it on here. There you go. And that's what it is. And no, it does not bind, even in the slightest, from the corners. Let me hold it. But you notice it tends to lean to one side. That's because I've got the magnet up on the side here. I'm going to put a string in this. Get that off there. It's because I got the magnet sort of cattywampus. And I did that intentionally so that I would have room in there for like shining a light through. But after much experimentation, I've decided to that little hole does almost nothing from a lighting perspective. So I'm just going to move the magnet back to the center, and that way I won't have this one corner that leans in a bit when you press on it. So that part's going to go away. But this one's very, very gentle force. This is the one I measured at like 30-ish, 30 something. and it doesn't bind at all. Not even remotely, and that's because the tolerance is 0.25. I could actually reduce the tolerance, and if you set the tolerance something really tight like 0.1, then you can just sand the stem until it's just perfect, the way you want it. But I'm way too lazy. I don't mind a little wobble. It doesn't matter. As long as it doesn't bind, that's all that really matters. And just like before, if you turn the spring and you turn it at a 45-degree angle, that it turns it from like a beam spring style force curve just to linear. This is straight up linear. And you lose about, I want to say like, not half the force, probably you lose 40% of the strength of the spring by turning it 45 degrees. And that's a feature because, when you want a linear switch, you want it to be nice and light, right? And since the Hall effect sensor and it uses analog, you'll be able to set the actuation point so you won't have to worry about accidentally actuating the switch. I don't know why that's blurry, but so that's the latest design. This is a 4mm travel, and it's 4mm precisely. I've had some problems with previous designs where it was like 3.8mm or 4.2 or way off, and like I actually printed one that had like an 8mm travel in it. But what's kind of neat about that is I could put 2 of these springs on the stem, and it worked just fine. I think that key switch is around here somewhere. No, I put it in my prototypes bag. Anyways, that's the latest 3D printable key switch design, and it should work fine. I've tested it on the breadboard with the Hall effect sensor, and I can easily detect 4mm of distance as long as the point where it ends is about at least 2mm above the actual sensor. But that's about it. I'm working on the PCB now, and I'll be changing the stem slightly where the magnet goes in. But that's about it.